Since our initial introduction to antiderivatives or indefinite integrals, we've looked at a variety of techniques that we can use to antidifferentiate various expressions. One such technique is partial fraction decomposition, and essentially what we're doing here is we're going to take a somewhat complex quotient of polynomials and we're going to write it in a way that is integrable, or we can take the antiderivative of. So if we have an expression like this and we want to integrate this, what we would do right now, or at least the only technique we know right now that might work, is to use substitution, and we can let u equal x squared minus 2x minus 15. That would be the denominator here. And then our du would be 2x minus 2 times dx. And we run into a problem here because this 2x minus 2 doesn't match up with the x minus 13, and there's no way to change that to 2x minus 2 and still allow us to integrate this. So substitution is not going to work here. So we need to find a different method, and the reason that this partial fraction decomposition works is because the denominator can be factored into what are called linear terms. So x squared minus 2x minus 15 is the same thing as x minus 5 times x plus 3. Now, since x squared minus 2x minus 15 can be factored, we're going to look at this as the sum of two separate fractions. We're going to write this as two partial fractions. And since the common denominator of these two fractions that I've started here will be x squared minus 2x minus 15, we want to figure out what our numerators will have to equal here to get this expression, this x minus 13 in the numerator there. So to do that, we'll go ahead and put just two variables in the numerators. We'll call them a and b. And to add these two fractions together then, we would end up with this. So to get a common denominator, we'd multiply this by x plus 3 over x plus 3, and we would end up with a times x plus 3, which we get right here. And this one we would multiply by x minus 5 times x minus 5, which we get right here. And so these two fractions added together will be equal to this. Now keep in mind that this right here, we are trying to replace the expression here that we want to integrate. So I'll write that over here, x minus 13 over x squared minus 2x minus 15. Since this denominator here is equivalent to this denominator here, this is just the factored form, then we know that the numerators will need to be equal to each other. And there's a little trick we can use to solve for a and b. Essentially what we're going to do is we're going to make this term right here equal to 0 by letting x equal negative 3, and then use that to solve for b. So if we let x equal negative 3, then plugging negative 3 in for x here, and plugging negative 3 in for x here, we get this, 0 plus b times negative 8 is equal to negative 16, and so that tells us that b is going to equal 2. And similarly, if we let x equal 5, then this term right here is going to be 0, because 5 minus 5 is 0, and so we plug 5 in here, with 5 minus 13 is negative 8, 5 plus 3 is positive 8, so we get a times 8 plus 0 equals negative 8, and so a equals negative 1. Now, knowing what a and b are here, we can rewrite this expression as negative 1 over x minus 5 plus 2 over x plus 3. These partial fractions right here add together to get our initial fraction, x minus 3 over x squared minus 2x minus 15. Now, with these two, we could integrate these separately. We could integrate this and we could integrate this using substitution because we have these linear terms in the denominator now. So let's look at how we would do that. If we wanted to integrate this expression, we would integrate the expression that we just got that we know is equal to it, and we can integrate each one of these separately. So we would take the integral of negative 1 over x minus 5 by substituting x minus 5 in for u, or u in for x minus 5, sorry, and we could substitute v in for x plus 3, so du is going to equal dx and dv equals dx by taking the derivative of each of those, and so we have negative 1 times the integral of 1 over u times du plus 2 times the integral of 1 over v times dv. we know the integral of 1 over u with respect to u is going to be the natural log of the absolute value of u, and likewise the integral of 1 over v is going to be the natural log of the absolute value of v. And then at this point we need to plug our u and v values back in, so we get negative natural log of x minus 5 plus 2 times the natural log of x plus 3. Now, it's generally good practice to write natural log answers as a single logarithm if we can. So what we'll do is manipulate this a little bit. We'll take the negative 1 coefficient here and we'll write that as an exponent. We'll take the 2 coefficient here and write that as an exponent. And we can actually change this constant here to the natural log of some constant also. So what we end up with is something that looks like this. Notice here that I use the absolute value of k here for our constant, and we can combine this into a single logarithm that would look like this using our laws of logarithms. Notice also that I removed the absolute values from this one right here, because if we take an expression and square it, it's going to have to be positive. And when we take x minus 5 to the negative 1 power, that x minus 5 is going to end up in the denominator. Now, we'll also run into some where we'll have to use partial fraction decomposition, but in this particular example, before we do, what we'll need to do here is we're going to need to make the numerator a smaller degree than the denominator. Partial fraction decomposition doesn't work for us in a case like this where the degree on top is larger than the degree on the bottom. So to do that, what we're going to do is long division. This simply means 4x cubed plus 8x divided by 2x squared minus x minus 1. So we're going to set up long division here. And keep in mind that when we do long division, we need to include every degree in the denominator. So we don't just need the x cubed and the x terms, but we also need the x squared and the linear or in the constant term. So we'll make those zeros, of course, and we're going to divide that by 2x squared minus x minus 1. And then we'll go through the long division process, and we end up with 2x plus 1 with a remainder of 11x plus 1. And so we rewrite this expression as the integral of 2x plus 1 plus 11x plus 1 over 2x squared minus x minus 1. Now, integrating this term by term, we know how to integrate 2x, we know how to integrate 1, and now we can use our new trick, the partial fraction decomposition, to rewrite this quotient as something that we can integrate. 2x squared minus x minus 1 factors to 2x plus 1 times x minus 1, so we'll rewrite this as two separate fractions. And we would have a over 2x plus 1 plus b over x minus 1, and we end up with a equals 3 and b equals 4. So this quotient right here is going to equal this right here, 3 over 2x plus 1 plus 4 over x minus 1. From this point now we can rewrite that as two separate fractions or two partial fractions. And now each one of these terms are terms that we know how to integrate. We can integrate the 2x, we can integrate the 1, and now we can integrate the 3 over 2x plus 1 by using substitution, and we can integrate the 4 over x minus 1 by using substitution also, substituting a variable like u or v for the expression that's in the denominator. And when we do that, we get x squared plus x plus 3 halves times the natural log of the absolute value of 2x plus 1 plus 4 times the natural log of x minus 1 plus a constant. Again, when we have natural logs involved, we want to combine them into a single natural log when we can. Keep in mind that these coefficients in front of the natural log become exponents. This is going to be 2x plus 1 raised to the third power, and then the square root of that, because it's a half power, and this is going to be x minus 1 raised to the fourth power. Since it's raised to an even power, we can remove the absolute values, since that even power will make it positive. And so we get a final answer then of x squared plus x plus the natural log of the square root of the absolute value of 2x plus 1 to the third power times x minus 1 to the fourth power plus c. If we had wanted to, we could have incorporated this constant into the natural log. And that's just a personal preference thing. You can if you would like. You don't have to if you don't.